Gibbs energy of reaction in electrochemical cell. Here we have a Daniell cell. In Daniell cell, negatively charged anode and positively charged cathode. Cathode having a reduction, anode having a oxidation. Now 2 moles of electron will flow through a wire on total 1 mole of zinc and 1 mole of copper reaction. So the 2 moles of electron will carry in total 2 moles into charge on 1 mole of electrons, which is 96,487 coulomb per mole charge. So 2 into 96,487 coulomb per mole is a total charge flowing through the wire. So for first work done, in terms of electrical work shall be said to be done 1 joule if 1 coulomb of charge move under a potential difference of 1 volt. Now, maximum work done by the galvanic cell is equal to decrease in its Gibbs energy, which is charge into EMF of the cell, which is equal to minus NFE. N is the number of moles of electrons, F is Faraday's constant, E is the EMF or cell voltage. Under equilibrium condition, the Gibbs energy change will be equal to minus NFE, standard electrode potential, which is standard cell potential here, equal to minus NF, substituting the value of standard cell potential at equilibrium, which is RT by NF log natural Kc, equilibrium constant. It is equal to minus RT log natural Kc. So the Gibbs free energy change in a cell will be given by is equilibrium constant. Higher the value of equilibrium constant, larger will be the free energy change. Now, conductance of electrolytic solutions. The conductive properties of solutions play an important role in analytical chemistry. It will help to assess concentration in solution quantitatively. Like we having a solution and we apply a known voltage across it, and ions will be start moving to their counter electrodes or oppositely charged electrodes. Here negative terminal is connected to one electrode, positive to another, and here it's looking like an electrolytic cell. So negative terminal will be anode, positive terminal will be negative terminal will be cathode, positive terminal will be anode. Before that, let's have standard definitions. First, electrical resistance of solutions. Electrical resistance of solution is measure of resistance offered by solutions to the flow of current through it, and it's proportional to the length, inversely proportional to the area of solution, and in that case the proportionality constant will be resistivity or rho. Like resistivity is a measure of resistance offered by solution to the flow of current through it. Conductance is the ease with which current can flow through a solution, and it is the inverse of resistance. Conductance, its unit is Sieman. Mho or inverse of ohm. G is a unit conductance representation is equal to 1 by R, as we know, inverse of resistance. So area per unit length and resistivity here, like inverse of resistance is conductance, inverse of resistivity is conductivity. So conductivity into area by length is, this unit is meter. So unit of conductivity will be Siemens meter, and conductivity into meter. So meter will goes to other side. So Sieman inverse of meter is unit of conductivity. And here area per unit length is known as cell constant. So conductance will be equal to cell constant into conductivity. Let's see certain conductivities of different materials, metals and solutions. Here we see a conductivity of sodium, gold, silver and copper. Among these we see metals, silver have a highest conductivity and copper have, which we use for all our electrical applications, having a little lower conductivity compared to silver, but still significantly higher than all other elements. And from that, if we look at why not we use silver for making all our electrical power transmission. Simple is silver is fairly costly compared to copper. That's why we are using copper only for laying down all our cables and all that. Next is insulators. We see their conductivity is very high. Now coming to aqueous solutions, like we see here, conductivity pure water 3.5 10 to minus 5. It's comparatively low. 0.1 HCl 3.91, roughly 1 lakh times higher, and 0.01 molar KCl 0.14. So we see conductivity of a pure water improves drastically when we add electrolytes to it, because electrolytes ionize and act as charge carrier. That's why these solutions are conductive. And in KCl, which is having a very low concentration 0.01, now here both solutions you see KCl and NaCl. KCl for same concentration is 0.14. Sodium chloride is 0.12. It depends upon the nature of electrolyte. Like here, HCl and acetic acid, same concentrations, but their conductivities are entirely different. HCl having a far greater conductivity than acetic acid because it furnishes ions more quickly in solution than acetic acid. Because of this, for same concentration, HCl is a better conductor. So nature of electrolyte, it depends upon the conductivity. On which conductivity depends. Next is we see KCl, NaCl. Chloride is the same on both, only potassium and sodium is different. Now both are strongly ionic, so from that point of view there is no difference. Both will furnish ions in solution and they have same concentration. Potassium chloride is still slightly better conductor than sodium chloride. The reason is sodium ion or sodium cation is smaller in size, so it getting a secondary shell around it. secondary shell of water ions. Because of its high polarizing capacity, it makes a hydrated shell. That hydrated shell makes the movement of sodium ion bit difficult, while potassium, having is larger in size, its polarizing power is not as strong as sodium. So potassium, what happens is secondary shell or the shell of hydrogen attached to it is not that great. That's why its relative size is small compared to small compared to sodium. So its movement in the applied electric field or between the electrodes is better. That is why its conductivity is slightly better. We can say effective size of potassium with the hydrated shell is small compared to sodium. So the size of the ions produced that also affect the conductivity, as we just saw here, case of sodium and potassium. Next, the nature of solvent and its viscosity. In case of like we're using a water in which having a lower viscosity than any of other solvent like glycerin or any other which having high viscosity, in that case conductivity will be lower in high viscous solvents. Low viscosity solvents having a better conductivity. And remember that solubility also matters. In the viscous or non-viscous solvents, the compounds or the salts should be soluble. Now, nature of solvents we discussed. Next is concentration of the electrolytes. Now, concentration having effect on the movement or ionization of electrolytes, and temperature. Obviously, temperature having a direct effect on the mobility of ions as well as the viscosity of solvent. So it also affects the conductance. Let's see a conductance and temperature graph. Usually it increases in a linear fashion, and after a certain temperature it will start plateauing. Now we will calculate conductivity of ionic solutions experimentally. For measuring the resistance of metals, a Wheatstone bridge is used, but we can't use the same method for solutions because it having a two problem. This is a Wheatstone bridge. These two resistance bottom resistances, and we having here potentiometer which will detect the current. When there is no reading, no current is flowing through it, it means Wheatstone bridge is balanced. The first challenge is, in Wheatstone bridge we pass a DC current, and DC current changes the composition of a solution. That's the problem. Passing a DC current through a solution can change its composition, so we will not get the accurate answer of conductivity. We can change it by passing an alternating current. So first problem can be sorted out using the AC. Next is, the second problem is, solutions cannot be connected to the bridge like a metallic wire because solution is a liquid state. How can we connect it? We can't connect it with the wire simply. That problem was sorted out using a conductivity cell. This is a conductivity cell having a 2 platinized electrode. Platinum, because they are inert, they will not react with the solution. And these, we fill this through this stopper, we fill a solution here. And we know the length of it, we know the area of it, so it's easy to measure. Now we put this conductivity cell in the 4th location. This is called a modified Wheatstone bridge. And R1, R2, R3 and R3 and R4. And we have a variable resistance R1. We adjust its resistivity such that there is no current pass through the detector. So when bridge is balanced, there is no current through the detector P. At this stage, the ratio of R1 to R2 and R3 to R4 will be equal. R1 by ratio R2 is equal to R3 by R4. So R2 by R, now R1 by R2, R3 by R4. We know these are variable resistance. We know R3 and R4 as well. So by knowing this, we can find the resistance of our solution. And inverse of resistance is conductance. So we know the conductance of solution. We know that length of cell. We know the area of cross section of cell. So even the cell constant we know. So conductivity of cell can be found using this conductivity cell. That's what we know, the resistance, that is rho by LA. Cell constant will be L by A per unit meter. 1 by rho is equal to cell constant into 1 by R2. So 1 by R2 is nothing but conductance into cell constant. So conductivity will be equal to conductance into cell constant. This was simple conductivity. Molar conductivity is when we consider the concentration effects. So it is defined as conductivity of solution per unit mole of solute dissolved in a given volume of solution. So molar conductivity will be, which is represented by delta M, equal to conductivity kappa divided by concentration. Its expression will be, we can convert into a moles per liter. The concentration here is mole per liter. We can convert it into a metric volume. This is a conductivity Sieman per meter. And we know here is a mole per liter, and we know 1000 liter per meter cube. So in this way, we are converted into a mole per meter cube by multiplying by 1000. So this is the expression for molar conductivity, and its unit will be Sieman meter square per mole. And so remember, 1 Sieman meter square per mole will be 10 to the power 4 Sieman centimeter square per mole.